Let's get started with lecture 8. So last time we talked about rolling without slipping. So we were thinking about some round object rolling on some flat surface, and we found that, well, if it's not slipping, there's no relative motion, and if the flat surface is stationary, then the instantaneous velocity of this point must be 0. So we had several pictures to understand this motion, but the important thing is we figured out that if the center has some velocity, let's call it VCM, and then the angular velocity omega, so the rate of change of, let's say, this angle here is omega, then we found that for a circle of radius r, we found that VCM is r omega. We also took a derivative of this to find that the acceleration of the center is r times alpha. Okay, so that was those were the two constraints that related the velocity and angular momentum, and similarly the acceleration and the angular acceleration when there is no slipping. Another observation was that at the point of contact, again, because there's zero velocity, any friction that's applied to our object is static friction, which doesn't do any work. All right, so today what we want to continue talking about is angular momentum. So we talked about many of the counterparts in the context of rotational motion for quantities we're familiar with. So momentum is the one quantity we haven't talked about, and as you can imagine, well, let's go back to our table and first let's take a guess about what the angular momentum would look like. So if we go back to this table here, let's say we had linear, we had rotational, so I just write a couple of the quantities we talked about. So for example, we had velocity and the rotational analog was omega. We had mass and the rotational analog was the moment of inertia. And if we have momentum, well, momentum in the context of linear motion is mass times the velocity. So what we expect here is a quantity which we call angular momentum that is I omega. Now, there is one issue that we kind of swept under the carpet in our discussion before. We're basically concerned in this course, at least, with planar motion. So our rotations have an axis whose direction doesn't change, right? All of the problems we've considered, we can basically consider an axis that's coming out of the plane. So we can have all the rotation occurring in one plane. That's, of course, a kind of a special case, right? A more general rotation, you can have your axis pointing in any direction in three-dimensional space, and then the axis itself can change direction. So that's a more complex dynamics, more general dynamics that's beyond the level of this course. Here we've been thinking about planar rotational motion, where if we look at the axis kind of from above, so we see the axis as a point, then we see our object just rotating in a plane. And that's fine, but there's something that that kind of gets lost in this. So for example, notice that the velocity is a vector, right? It has a direction. Angular velocity, when we were talking about angular velocity, so going back to this, we just defined a sign. We didn't really discuss having a vector that points in any direction, right? We just said, well, you look from the top, you have some object, let's say this is your axis. And then if the rotation is counterclockwise, we say omega is positive. If the rotation is clockwise, we say omega is negative. We did something similar for torque, right? We said if your torque wants to rotate the object counterclockwise, we say it's positive. And if it wants to, if it has a tendency to rotate the object clockwise, we say it's negative. So somehow it may make sense to associate a vector to this, but where would that vector be? So it turns out it's very useful to define a vector coming out of the plane perpendicular to the plane, parallel to the axis, and then the direction of that vector can be either coming out of the page or going into the page, depending on whether you're rotating counterclockwise or clockwise. So we can define angular momentum, angular velocity. We'll get to angular momentum in a little bit. Angular velocity and torque vectors. So how do we do that? Well, let's say consider, this object is rotating counterclockwise. So we can use the right-hand rules, put our thumb in the direction of this vector, and then the rotation of our fingers gives us the direction of rotation. So, and similarly we can do, so if you're going the other way, rotating clockwise, you can imagine this thing going down. So this is a vector angular velocity that's in the direction of the axis of rotation, perpendicular to the plane in which the rotation occurs. So this is a better figure with a picture of the hand and the thumb in the direction of the rotation. So we can define this vector whose length, whose magnitude is the absolute value of omega we calculated. And then if the rotation is counterclockwise, it's coming out of the plane. So it's really putting your thumb in the direction of this vector. Then the way you kind of bend your fingers to make a fist, that rotation of the tips of your fingers kind of represents the direction of rotation, as shown in this figure here. Okay, now you may have realized that this sounds a lot like the thing you've already encountered when you were studying magnetism, right? The force, for example, due to a magnetic field, or the magnetic field generated by a moving charge, or the magnetic field generated by a current, which is a bunch of moving charges. So the mathematical structure that appears in this is something called the cross product of two vectors. So so you're familiar with the cross product from 162. I don't want to spend too much time on just the kind of mathematical mechanics of how to do this. So we had this right-hand rule again. So one way is, this way you put your thumb in the direction of the first vector, your index finger in the direction of the second, and then your middle finger represents the cross product A cross B. Or we can think about this other way. So you put, let's say, your fingers in the direction of A, and then the direction you close your fingers is B, and then your thumb gives you A cross B. Now, then this allows us to relate torque to force in a more elegant and compact way. So let me go back to the notes here. So similarly, suppose, let's go back to the notion of torque. So you have, let's say, some axis here. There's some distance r to the place where some force is applied. There's some angle theta. So the way we defined torque was, well, we said you take the component of the force that's perpendicular to the arm of rotation, to this line that connects the point where the force is applied to the axis of rotation and is perpendicular to the axis. And that component is going to be this component here. So that has a length f sine theta. And then we multiply this perpendicular component by r. And then we say if it wants to rotate clockwise, we put a plus sign. If it wants to rotate counterclockwise, we put a minus sign. So now our torque would be, if I go into this plane, let's say now this is my axis here. This is r. This is my force F. So this is a counterclockwise rotation. So then according to the right-hand rule, it must come out of the plane, right? If you put your right-hand thumb in the direction of this vector, then the closing of your fingers represents this rotation. So the vector tau is a vector in that direction whose length is r f sine theta. But that's precisely according to the definition of the cross product, that's r cross f. So that's a useful kind of vectorial definition of torque. This leads us to define the angular momentum vector. So let's consider, let's say, again, this is our axis, and let's consider a particle that's moving with some arbitrary velocity on this plane. So it's at position r, and it has, let me draw the momentum vector, right? So, which is basically the velocity vector times its mass. So it has this in-plane momentum. Now, going from force, which was the linear thing, to angular momentum, we multiplied that by r. So let me just define angular momentum L as L being the cross product of r times p. Okay, so how can we make sense of this or build some intuition about what it means? Well, you see, this definition does two things, right? So one is it kills the component of momentum in the radial direction, right? Because the cross product is a vector perpendicular to both, so it's going to be a vector perpendicular to the plane, coming out of the plane in the direction of the axis, whose length is r times the component of momentum perpendicular to r. So that means if I decompose my momentum into a component in the radial direction and a component perpendicular to that direction, this component does not really contribute to the angular momentum. All the contribution of momentum to the angular momentum comes from this component that's perpendicular to r. Right, that's good because that's what can give us rotation, right? So suppose, you know, you're moving in some radial direction. Let's say this angle, we call it with some fixed axis, we call it theta. If you just keep moving on this radial direction, you're not changing theta. So in some sense, it makes sense that you have zero angular velocity, right? The angular velocity was the rate of change of theta. We defined it for just perfect circular motion, as you're just rotating around the fixed axis. You don't have any motion in the radial direction. But if you do, if you have a more general velocity, well, there's part of it that's in the radial direction, and that doesn't change the angle. And there's some part of it in general that's perpendicular, and that changes your angular position. So it contributes to your angular velocity. So that's a nice feature of this definition, that the component in the radial direction that doesn't contribute to angular velocity doesn't do anything. Okay. Now, what else can we say? Another thing we can talk about is, let's write it this way. Write momentum as mass times velocity. So mass is just a scalar number, so I bring it up front. And then this, you know, if you have the perfect rotation, right? So if suppose you're rotating, suppose you have a particle of mass m rotating around the perfect circle. We've already killed this radial component, so let's not worry about it. Particle of mass m rotating with angular velocity omega, right? So it's doing a perfect rotation with angular velocity omega. Well, then the length of v, the vector v is always tangent to this circle, right? And has a length equal to r omega. So what are we going to get? So we have, let's say in this special case, we have the vector r here, and we have a vector perpendicular to it, right? Tangent to the circle is perpendicular to the radius, whose length is r omega. So let's call this, I don't know, v, such that the length is r omega, the length of the vector r times omega. Okay, now if I find this cross product, it's going to come out of the plane. So r cross v is a vector who's coming out of the plane, and then it has a length, because they're just perpendicular, is just the length of this vector r times the length of that vector v, which is r squared omega, right? Now for the case of perfect rotation, the angular velocity vector is coming out of the plane and has a length that is just mass times that, right? L is m times r cross omega. So the length is mr squared times omega. And this is the moment of inertia of a point particle, right? So now if you have a whole bunch of point particles, omega is the same for all of them. So the angular momentum vector just becomes a vector in the direction of the axis of rotation. axis of rotation. So let's say you have rotation with fixed axis, then L is a vector in that direction whose magnitude, whose length, is simply I omega. So this ties in with the moment of inertia being the analog of mass and omega being the counterpart of v, velocity. All right, so this is a very natural and useful definition of angular momentum. Now, of course, you can guess another equation, right? So remember going to our table, keep repeating this, but it's good to have this analogy in mind. Let's say linear rotational. So velocity, omega, acceleration, angular acceleration, mass, moment of inertia, force, torque, and we already had an equation F equal ma whose counterpart is tau is equal to I alpha. And then F equal ma we can write in a different form, right? We can write F is dp dt. And then you see that the way we define the vector tau and the vector L allows us to keep the same equation. So we find the vector tau, which was defined perpendicular to the plane in the axis of rotation, is just the rate of change of this velocity, of this angular momentum vector, right? They were both defined perpendicular to the plane of rotation. So we have, let's say L is R cross V. And then if I take the derivative of this, well, it's going to be the derivative of the first one cross V this was defined with a mass. Mass doesn't change. Plus the derivative plus R cross the derivative of the second one. Okay. So this gives me mv cross v plus R. M times a, dv dt is the acceleration, is the force, right? So this is the vector tau, the torque vector in the way that we defined it, and this is 0, right? When you take the cross product of two vectors, we take the component of one that's perpendicular to the other and multiply the length. Now, if they're the same vector or in the same direction, well, they're in the same direction, so one doesn't have any component perpendicular to the other. All right. Now, the next thing, which is a direct consequence of this, is something called the conservation of angular momentum. So let me remind you from 161 what was momentum conservation, right? The conservation of momentum said if you have a system and there is no net force acting on it, then because the net force is the rate of change of the total momentum, then if the net force is 0, the rate of change of the total momentum is 0. So the net momentum does not change, right, in the absence of net force. Now, the conservation of angular momentum is very much similar to that. So if we have a system such that net torque is 0, we get 0 is the rate of change of the angular momentum with respect to time. Therefore, L is constant. Very easy to state, and it's quite powerful in solving problems. So let's look at one problem, and I'll give you some time to think about it. So take a piece of paper and a pen and try to work this problem all the way through using the conservation of angular momentum. So here's the problem. Right. So that's the statement of the conservation of angular momentum. And now here's the problem. So we have a 20 centimeter diameter, 2 kilogram solid disk that's rotating at a certain RPM. So this disk at the bottom is just rotating. And then a 20 centimeter diameter, 1 kilogram circular loop is dropped straight down onto this rotating disk. So then friction causes the loop to accelerate until it's riding on the disk. That means they're moving together, right? They acquire the same final velocity. So we want to find this, they acquire the same final angular velocity. So we want to find this final angular velocity omega f. Yeah, take a few minutes and take as much as you need. Try to work this problem all the way to the end. All right, so let's think about this problem now. Just check what the, yeah, example 1219. So here it is. So example 1219. So what's happening? So we have this disk that's rotating with some angular velocity, let's say omega initial. And then we have this ring up here that just drops on top of it, right? So what is the angular momentum of the disk? Well, it has an angular momentum, let's say L disk is I disk, the moment of inertia of the disk around its center, right? It's rotating around an axis, it's going through the center, times omega I. That's the initial angular momentum of the disk. What about this guy? So it has velocities that go down, right? All the velocities of different pieces of this ring are parallel to the axis. So there is no rotation around that axis, right? Therefore, the angular momentum in the direction of the axis in this vertical rotation is 0. So let's call it ring is 0. Now what happens? Well, it falls down on the disk. There's some friction. Initially, when it hits the disk, it just stops and the disk is going, so they're slipping against each other. But then the friction between the two makes the ring kind of accelerate or angularly accelerate. And ultimately, when they stop slipping, there is no relative motion between the two. Both of them will have the same angular velocity. Okay. So in this whole process, is there any external torque acting on the system of disk plus the ring? Not really, right? There is no external force. If the axis that goes through the disk is frictionless, which is our assumption, because previously it was just rotating at constant angular velocity omega, so there can't be any torque before. So that axis by assumption is frictionless. There's no external forces on this system to exert a force. There's no in-plane. I mean, the only thing is maybe gravity, but that's not in the plane of rotation. So yeah, so there is no external torque. So we can say tau net is 0. Okay, so that's, let's say, initial. What about the final configuration? So when they come to rest relative to each other, when there's no relative motion between the two, well, the disk will be rotating at angular velocity omega f. The ring, which is sitting on top of the disk here, will also be rotating at omega f. So therefore, the angular momentum of the ring is going to be the moment of inertia of the ring times omega f. The angular momentum of the disk is the moment of inertia of the disk times omega f. So if total momentum is conserved, total angular momentum is conserved, conservation of angular momentum, well, I can write the total initial angular momentum, which is ring plus the disk, but ring has 0, so it's just moment of inertia of the disk times omega I is the total final angular momentum, which is I disk plus I ring, which is the moment of inertia of the combined system of the ring plus disk times omega f. So it's a very simple equation, right? Initially, only the disk is rotating, so the total angular momentum is the moment of inertia of disk times the initial angular velocity. And then that must be equal to the final angular momentum, which is, because both of them are rotating, which is the total moment of inertia times the final angular velocity. So from here we find omega f is I disk over disk plus ring times omega I. All right, so now we just look back at what these things are. So if a disk of mass m and radius r rotates around its center, it has a moment of inertia. We can look it up in the table. I believe it's 1/2 mass times radius squared. And the ring, all the masses at distance r, so there is no factor. It's just the mass of the ring times r squared. So plug in these into our equation above. We find omega f is the factors of r squared cancel out. So we get m disk 1/2 m disk plus m ring omega I rather, the initial angular velocity of the disk. So this is just 1. If we divide the denominator and numerator by 1/2 m disk, so I get 1 here, and here we get 2 m ring over m disk. All right, a relatively simple problem. So we can take a look at the numbers now. So let's go over the solution together. Yeah, basically the same story. All right, so here's a quick question. So again, take a few moments or a minute or so. Think about the answer, and then we come back and go over it together. Okay, so we have two buckets that spin around the horizontal circle on frictionless bearings, and then it starts to rain. So the raindrops are coming down vertically. Again, they don't have any in-plane velocity, right? So they don't have any angular momentum around this axis where the buckets are rotating. So then they fall into the buckets, and they will rotate with the buckets. Now, so again, it's a conservation of angular momentum problem, right? There's no external torque on the system of raindrops plus buckets, so their total angular momentum must be conserved. So initially only the buckets are rotating, the raindrops are not, and finally they're rotating together. So the moment of inertia has gone up, the moment of inertia for the thing that's rotating, right? Initially we just have the moment of inertia of the buckets. Finally we have the moment of inertia of the buckets plus the rain accumulated in the buckets. And therefore the angular velocity of the buckets must come down to conserve the angular momentum. Let's also think about why the other problems are wrong, right? So it doesn't speed up, it slows down. So A and B are incorrect. Yeah, they're all obviously incorrect. I mean, they have the wrong prediction. All right. Okay, so we're done with chapter 12. I think we covered everything in this chapter from section 1 to section 11, 12, 11. The only thing we didn't talk about was an advanced topic, I think section 12.12 on the gyroscope. So yeah, we're not discussing this. So let's have a brief review or summary of the contents of this chapter. So one important equation we talked about was Newton's second law for rotational dynamics. We talked about what a rigid body was, the model of the rigid body. We talked about alpha being the net torque divided by the moment of inertia. We define things like the center of mass, the moment of inertia around different axes. We talked about the parallel axis theorem, for example, in the context of calculating the moment of inertia. We had some energy conservation considerations, right? So if you have pure rotation with a fixed axis, your rotational energy is 1/2 I omega squared, and then the change in potential energy would be as if all the mass m is at the center of mass. If you have rolling, then you add the rotational kinetic energy to the translational kinetic energy of the center of mass. And then we had the constraint that VCM is R omega. We defined the angular momentum. So it turned out that it's equal to I times omega. And if the net torque is 0, then the rate of change of angular momentum is 0. So angular momentum is conserved. We defined torque. Again, we had like a simple definition. We had two ways to visualize this, right? The distance that from the axis to the line where the force is applied, or taking the vertical component of the force to the arm of rotation. We also had the vectorial definition in terms of a cross product, so it's a vector that's perpendicular to the plane of rotation parallel to the axis. Yeah, another representation of Newton's second law for rotation. Definition of the center of mass, definition of the moment of inertia, rigid body model. We talked about equilibrium, static equilibrium, which was a special case where there's no net force and no net torque because there is no acceleration for the center of mass and there's no angular acceleration. And yeah, so we had this constraint for rolling motion. We also had some constraints for ropes and pulleys that were similar. So I think this is a good place to stop this last lecture of chapter 12. So what's coming next, we're going to jump to chapter 15 on oscillation. And in the chapter on oscillations, we'll talk about simple harmonic motion. So basically, you have a sinusoidal dependence on time and how it arises, the nature of the forces that give rise to that. So it comes out of forces that have a linear dependence on displacement. We have a couple of examples like a pendulum and masses on springs. So it's going to be a shorter chapter, and I think we'll probably need around a week to cover the next topic.